Okay, so we're starting with a new chapter, that is practical electricity. So first we have to look at what are the uses of electricity, right? Where do we use that in real life? So we use them as, or we use the electrical power as electric heating, right? Just a moment. We use it as electrical heating, okay, and we use it as for electric kettle, we use it for electric iron, we use it for electric radiator. And electric radiator is basically an electric heater that we use in winters, right? So you may read about the details, but right now the topic is about utilization. Okay, so electric kettle, then we have electric iron that we use to press our clothes, right? Okay, so the next usage we have is with the filament lamp. Okay, and the interesting thing about the filament lamp is that how we actually make it or how we actually construct it. Do you remember that we did this last time? Resistance is proportional to rho L over A. Rho was the resistivity and L is the length of the conductor and A is the cross-sectional area. What they deliberately do is, if you zoom into this filament lamp or this filament, then what they've done is deliberately increase the length of this filament lamp by giving it more number of turns and more number of coils as much as possible. So it's not only coiled like this, it's also coiled in its own position like this, just to increase the length of that wire. So if we increase the length of that wire greatly, then the resistance of that wire increases greatly. And as a result, if the resistance is too high, then whatever amount of current that tries to pass through it will produce, or will generally produce, a heating effect. That heating effect eventually, when is exaggerated in that certain situation, becomes so high that it starts glowing and starts giving off us light. So previously we used to have this, you can say we had these type of bulbs and filament lamps, but they are not recommended because they waste a lot of energy as heat, because we are designing it to produce light, but they are wasting energy in terms of heat, so it's not a very efficient form of producing light. So then we shifted to incandescent lamps, fluorescent lamps, and finally on LEDs. We've settled down on LEDs. They use the least amount of power, produce the least amount of heat, and eventually give approximately the same amount of light energy. So we generally shifted towards that. So again, this is a fluorescent lamp, and so on and so forth. You can read about this when I'm going to share the slide with you. So you may read about the advantages and disadvantages of filament lamp and fluorescent lamp. It basically mainly the benefit is about the cost, and the only negative side is the energy loss, and vice versa is for the fluorescent lamp. So these are some motors. We use electric motors in our houses as well. You may see that when you're using an air conditioner, the blower that is inside that air conditioner is actually a DC or electrical motor that is actually rotating that fan. The fan that you have in your ceiling or on your ceiling in your house is also a motor. Now all these things are going to come in the syllabus of grade 11 when we're going to start with electromagnetism. That is going to come after this. So until then, we're just going to see that electrical energy is used to rotate, or you can say that we are using electrical energy to produce rotation or design machines that actually do rotate. So at the end of the day, we are using that electrical energy for electric motors as well. But the detail, how do we actually the motors work and how do they actually work, that's not a part of the course right now. It will be in the next chapter surely. Okay, so again, a few more uses of electrical energy: laptop charging, mobile phone charging, heating, cooling, lighting, right? Okay, so this is where the actual chapter, you can say, actually starts from. So there are 2 to 3 new formulas for this chapter that are universal for complete physics in terms of electrical power. You see, we have the formulas that we've done so far are V equals to IR, right? And we have looked into parallel series configuration. We have looked at I equals to Q by T, and we've also looked at V equals to work done by charge. These are the formulas that we've done so far. So the new formula, the new addition in electrical power or in electrical chapter, is the electrical power that we calculate as IV, current through the appliance multiplied by the voltage across that appliance. Similarly, the same formula can be replaced as, or can be written as, V square over R, and same formula can be written as I square R. And of course what we're doing right now for these separate implementations is we are just rearranging V equals to IR and substituting that in P equals to IV. So when we substitute that in two configurations, we get two formulas. The first one is this one and the second one is this one. Right? Do you understand this point?
Yeah.
Okay. All right, so, and in grade 9 chapters you can see that the chapter for work, power, energy, what we've done is power is equal to energy divided by time, right? So if I take time over there, what I can get is that energy or work done is basically equal to power multiplied by time. So I have these three formulas for electrical power. I can just simply replace them and get multiple equations for electrical energy that my appliance may use when we're operating it, be that air conditioner, be that laptop, be that anything. So it would become IVT, it would become I square RT, and it would become V square over R multiplied by T. Any issues in the formulation of these equations? And all of them are for the energy, and these are for the power, right?
And these last three that you've written, the rearrangements of the original one for
Exactly,
electrical power.
exactly. So I'm just
Okay.
putting in first form, I'm just putting in IV, and then I'm putting in V square over R, and then I'm putting in I square R. The
And
time,
by electrical current means how much electrical energy is like going
no, no,
through
no,
a
no,
current.
no, no, the simply the current, electrical current that we studied at the very beginning of the chapter. And of course, when the current flows through the circuit, it has some voltage as well, that is the energy of electron. Current is the flow of charges, how many electrons. Voltage is the energy of electron. The concept remains the same throughout the chapter that we started with. Okay? Alright. So, for example, if you have an air conditioner, let's say that this is an air conditioner. So, if I know that it is, let's say, 1500 watts and takes in 1500 watts of power and operates on a voltage of 220 volts. Here in Pakistan, we have 220 volts, so right? So, I can find out the current that it would demand from the source by simply using the formula P equals to IV. I know the power requirement of my appliance. I know what voltage it's operating at, so I can simply find out the electrical current it's going to demand from the source. So 1500 divided by 220, that will be I. And whatever answer that would be, it would be in amperes. So that is exactly the same amount of current, or the same current that we have done in the previous chapter, or the same aspect, or the same visualization, or the same understanding of the current that we did in DC circuit analysis. It's the same. There's only one difference. We can say that these are basically AC appliances and they're using AC electrical energy, and we've also understood what is the difference between AC and DC. But right now we're not interested in the distinction between AC and DC. We're more interested in the energy consumption. We're more interested in how much energy it will consume, so that we can at least calculate the bill of the consumer. And of course we can cut down on our energy consumption if, let's say, the billing is too high, or at least we are running out of resources, so we need to move towards more efficient appliances. Alright, so do we understand the formulas? Any problems?
Understand.
Okay, so now we're going to introduce a new unit of electrical energy. Previously, the energy's unit was simply joules. And the problem with this unit is that when you try to use that unit for electrical appliances, the answers become so large that they are inconvenient to deal with. Now just imagine that the energy consumption of a full house that is using, let's say, 5000 watts per day, or you can say per second, with a running air conditioner, with a washing machine, with a TV, with a laptop, and a few things on charging and everything else. So the average load of one house is considered to be 5 kilowatts. Now 5 kilowatts means 5000 watts, and 5000 watts again in base units would mean 5000 joules per second. So my house, or that respective house, of course it's going to change throughout the day, but we're talking about the average. So it's going to count, or it's going to measure 5,000 joules per second. There are numerous seconds in one day. So the calculated value by the end of the day will be so large that it will become inconvenient for us to deal with that. So what we've done is that instead of joules for this chapter, we've introduced a new unit for electrical energy, and that is kilowatt hours. Now let's try to see whether this is the same unit or not. So if I go back, now the unit is kilowatt hours. So the formula is power is equal to energy divided by time. Let's take time over there. So energy is equal to power multiplied by time. What is the unit of power? That is watts. What is the unit for time? That is seconds. So what we have done so far to reduce the numerical answers is that created watts, or changed watts to be kilowatts, and changed seconds to be in hours. So kilowatt hours is basically another unit of energy, but it is much larger in comparison. It gives us much larger values. Let's try to go back and try to make a simple calculation for the sake of this understanding. Let's say that we have an electrical appliance that is the same that we were using at that point, 1500 watts. Let's say it is 1500 watts and it is being used for, let's say, 10 hours per day, right? What I want you to find out is its energy in kilowatt hours, and I want you to find out its energy in joules. And let's see which one comes out to be more convenient in terms of values. So the energy consumption, because for this joules, I'll have to convert hours into seconds. So power, that is 1500, multiplied by seconds of 10 hours, that would be 10 multiplied by 3600. I'll get my answer, and over here I'll have to convert my power into kilowatts according to the unit. So 1500 divided by 1000. I'm dividing this by 1000. I'm going to do that every single time because I want to convert watts to kilowatts, and then I'm going to multiply this. Now since this is the power, multiplying this with the time will give me the energy. So the time that is operated, or it is being operated for, is 10 hours. And since the unit represents kilowatts and hours, I'm not going to convert hours into another unit because hours is itself the part of the same unit. So that will be 1.5 multiplied by 10, that is going to be 15 kilowatt hours of energy. This is what your electrical company bills you for. But anyways, let's look at the larger unit that we have over here. Have you calculated the value for this 1500 into 10 into 3600?
Yeah.
So 10 multiplied by 3600.
Quite large number.
It's going to be 54 megajoules. 54 into 10 raised to power 6 joules,
Yeah, that's
or 54 megajoules, right? So this is just one appliance that you operate. This is just an air conditioner that you used for one day for 10 hours, and look at how large the value is, how inconveniently large this is. And look at this value, this is just 15, right? So this has 6 zeros and this one has none, but they do represent the same thing. They do represent the same energy consumption by the same appliance. So this unit is basically, in simple mathematics or in simple layman terms, we can say that the unit is larger and this unit is smaller. It can be used to represent large quantities of power or large consumption of energy, and the joules can be used for smaller energy changes or smaller, more convenient formats of energy exchanges. So do we understand the new unit of electrical power and why did we make it? Why is the need for this electrical unit? Do we understand that? So let's move on to this example. So again, be very careful about this. We've done these formulas already. Okay, power is energy by time and voltage is work done by charge. We've done most of them. The derivation is not a part of the course. If you want to try it, it's your choice. You can do that. So the finally ultimate formula that we land is at P equals to IV, right? Okay, so again, these formulas, we've just looked at them. P is equal to IV, I square R, and B square over R, right? I'll just show you the implementation of just one. So if V is equal to IR and P is equal to IV, I'm going to replace V over here. So what I get is I into IR, so that becomes I square R, right? You can try this for V square over R, that would be your choice. But the derivation is not going to be asked from you. what they would ask you is to implement or use these formulas at least. The primary formula is VI or IV. The other formulas are secondary in terms of their nature, that if voltage is not given and you know the current and you know the resistance of the appliance, then you can simply directly find out the power without calculating the voltage. Although you can find out the voltage as well by applying V equals to IR, but it won't be asked from you. And if the voltage is given to you and the resistance is given to you, but the current is not, then you can again find out the power and you will end up getting the same answers as V equals to P is equal to IV. So it's just a matter of availability of the values, not a matter of special cases. If, for example, if voltage is not given to you, then naturally I'll have to use the formula, this is the second one. If the current is not given to me, then I'll have to use the third formula. And of course, we can find out the current and voltage in both cases, but that would add an extra step by using V equals to IR, which has no extra credit. So we will resort to these formulas or these ideas if we already know that one of the values is missing. If both are available, then we can directly apply P is equal to IV, right? So it's just a matter of convenience and the availability of values. Alright, so this table represents the average electrical powers of electrical iron. Let me write down the value. So from 950 watts, it will range up to 1200 watts. The LCD TV is approximately 120 watts, 125 watts, but they have reduced it down to approximately 100 watts. Fluorescent lamp 32 to, you will find them up to 400 watts that they use for floodlights, right? And electric kettle is generally ranging from 2000 watts to 2.5 depending upon how quickly it tries to warm or heat up water. You'll find the same ratings written down on the electric heaters that you buy for the room or for the house, and even for the air conditioners, because what they're trying to tell you is that how quickly this is going to do that job. So a more powerful appliance will do that job more quickly, but of course will use up more energy in doing so. So 2000 watts means a consumption of 2000 joules every second that you're going to run that appliance for. So higher the watt count or higher the wattage, higher will be the power consumption, higher will be the electricity bill, and so on and so forth. Okay, so we can see this, that he has connected a flashlight to 3-volt battery, negligible internal resistance, and shows a reading of 0.7 amperes. What is electrical power? You see, voltage is given, current is given. I'm only going to use IV directly. I don't have to use I square R, or I don't have to use V square over R. The resistance is not given to me. I could have found it, but I don't need to find it because I can apply V equals to IR. I can replace the voltage, I can replace the current, I can find the resistance. But that would add an extra step to my question. The resistance is not asked, it doesn't add to any benefit of my question, so I don't need to find it. I can directly apply this formula, so 3 multiplied by 0.7. So what do I get? I get 2.1 volts. 2.1 watts, sorry. Right? Do we understand the implementation of the formulas? And what are we thinking when we're applying? Exactly.
Which parameter we have.
Yeah. Yep. Alright. And again, they're coming down to the electrical energy formula that we just did. That is simply multiplying this with the variable of time. We're going to get the same answers again. Okay. So over here we have resistance as well. In this question, let's say, he tells me that an electrical iron with a heating element resistance of 60 ohms. Now I have the resistance for my question connected to 240 means. So the voltage I have is 240 volts. He's asking me to calculate the electrical power. So naturally I'm going to use the formula, that is V square over R. Current is not given to me. I can find it out by using V equals to IR, but again, it doesn't serve any purpose to me. So I'm simply required to square the value of 240 divided by 60, and I'll find out my power in watts. That he has done in the next part as 960 watts. Right? So this, my answer will be 960. Of course, it may be 957, 956. It may be over that. We have not calculated it. But he's converting that into two significant figures. Right? Okay. And then he says the amount of electrical energy consumed when operating the iron for 20 minutes. Now, this is an ambiguous question. He could have mentioned, or he should have mentioned, that are we supposed to find it in joules, or are we supposed to find it in kilowatt hours? Now, since we are dealing with this chapter, I'm going to find this in kilowatt hours because we are preferring, or it's preferable to use the larger unit that shrinks the values down instead of using a smaller unit that actually gives us a bigger answer. So the logic behind this remains the same. What I'm supposed to do is I'm supposed to convert all powers from watts to kilowatts, and all times, whatever unit they are given in, I'm supposed to convert them in hours, because the unit is kilowatt hours. So the energy consumption would be 960 dividing this by 1000 converts this to kilowatts, and I'm using it for 20 minutes. I have to convert this into hours. So 20 divided by 60, so that would be the respective number of hours this appliance was used for. So I can just simply find this out. So that would be 196 multiplied by, so that comes out as 0.32 kilowatt hours. If I had found this in joules, it would have been a larger answer.
Okay.
Acceptable? Right?
Yeah.
Okay, good, thank you. So you can see that he found this by converting this into joules, and look at the answer, how big that answer is. So it's inconvenient. The electrical supply companies, they cannot measure such large values. So it's impractical to measure such large values for just a single appliance. So they resorted towards kilowatt hours. That is a bigger unit. So look at 0.32 in terms of 1.15 megajoules. So this value is more convenient to work with rather than having a value that is 1.15. Do we agree at this point?
Generally, if you got a question like this and it's not stated if you're supposed to use
He will
joules
state
or
you. He will
kilowatts,
state you. If he
you
doesn't, okay. So if he doesn't state what unit is required, then the preferred unit is joules. If he does, and if you are dealing with this chapter, you will develop the sense of the question while you're solving the question, that this chapter demands your answers in kilowatt hours. Because when you're dealing with appliances, their energy calculations, how much bill you're going to get, so you will develop, or you will get that sense that this requires my answer to be in kilowatt hours, right?
generally, I guess that.
So this is another numerical question. You can try this on your own time, and I'm sure that we understand this as well, right? Okay. So again, this is an example that he is giving you power, he is giving you time of operation. Now since that is in kilowatts and that is in hours already, we don't need to convert anything, we're just supposed to multiply both of them. And over here he's doing the same exercise again that we just did, that instead of writing down 3 kilowatt hours, we have 1.1 power 7 joules. So again, based on convenience, we will use this unit for the calculations of larger situations. For example, the calculation of a full building, the energy consumption of, let's say, one street that has 10 to 20 houses, right? Okay. So this is what a respective or an electrical bill may look like. What you may do for your house as well, you may try this, or you may try to find this. You will find this unit in the bill of your house. This actually tells you how much energy that you've consumed in this month, right? And you can identify the appliances in your house that actually use the maximum amount of power, and you may reduce their usage, and you can just try this on your own, and you will find out that the next month or the incoming month your usage would have reduced. And it's always a good practice, not just because it's getting expensive, just because for the environment it's a good practice to be more efficient, or at least not use what is not required in that situation. Turning off the electricity lights, turning off the fans, or at least keeping those rooms closed that are not being used. And of course the solution is to switch to solar eventually, but that's a bit expensive right now. Okay. Again, all of these examples are representing the same idea that we just did, right? Okay. Okay. Now, this is what an electrical energy meter looks like. This is a very local brand, of course, made in China. But you may find such a meter outside your house. Have you seen this example, or have you seen this or something like that in your house, or outside your house for the electric supply company? Let's try to practice one example. For example, for an average house, let's try to calculate the bill of an average house. Okay, so we are using the air conditioner that is 1500 watts. Oh, sorry, 15,000. I've written down, so it's 1500, and I'm using it for 5 hours per day. Then we have the chargers, the laptop, the mobile phones. Let's say they are using 100 watts, and I'm charging, or let's say I'm using such an appliance for approximately 6 hours per day. The lights and the lamp, or let's say 500 watts, scattered around the house, and I'm using them for 3 hours per day. And let's say we have fan or fans, and they're approximately 1000 watts scattered around the house, and I'm using them for, let's say, 15 hours per day. And of course you can include the heater and the heating equipment that you may have in your house in this calculation, but for the sake of understanding, I'm not doing that right now. Okay, so if the electric supply company charges you 20 cents per kilowatt hour, right? So how much bill you're going to get after 30 days if you continuously use these things every day? So these are all the conditions of one day. I'm supposed to multiply that with 30 at the end of the calculation. But consider this: what students generally do is that they add all the powers together, they add all the times together, and then they solve the question. That would be wrong. We're supposed to solve them individually. We're supposed to find their energy consumptions individually. Then we're going to add them together, right? So for air conditioner, I'm writing this down directly. So that is 1500 watts. So 1500 divided by 1000 multiplied by 5 hours per day. So I don't need to convert that. Plus my laptop and chargers, 100 divided by 1000 multiplied by 6 hours consumption per day. The lights of my house are 500 watts divided by 1000 multiplied by 3 hours consumption per day. And then we have fans that I'm using as, although that's a gross, you can say a very high exaggeration. Fans are not this powerful or not power hungry as much as this one, but for the sake of example, of course, and we're using it for 15 hours per day. I'm going to mention the appliances again for your understanding, although it's not required by the examiner. So this is my air conditioner, this is my laptop and chargers, mobile phone charger, everything, even the Wi-Fi router or the other things as well. So this is my lighting load, and these are my fan of my house. And of course you can add more load, counting the number of things that you're using in your house. Do you understand that we have to solve them individually? We can't just add them, all of them together. We have to solve them individually. Okay. So now what I'm going to get is my combined kilowatt hours usage for one day, because I haven't even multiplied the 30 with any of the factors. I'm just finding it for one day. So I'm going to use the calculator to find out these values right now. So my usage of one day is coming out as 24.6 kilowatt hours. Did you get the same answer for one day? And now if I multiply this with, okay, 30, what I'm going to get is 738 units, or 738 kilowatt hours. You may see that for a layman, for a common man, these kilowatt hours are generally referred as the unit. You may hear people talking about that the electricity is getting expensive. The unit cost of electricity is getting expensive. So that one unit is basically this kilowatt hour, or the rate quoted by the company. This is what they're trying to increase. So that if one unit cost increases, the total multiplicity or the total final answer will also increase. So if 20 cents is my answer, so let's convert 20 cents already to dollars, so that my answer can be found in dollars, because I'm expecting a very big answer at this point. So 738 answers, so 738 units per month, or 738 kilowatts per month multiplied by 0.2. My bill or electrical bill should be $147.6, and approximately this should be $150. And of course this is just the cost of electricity. I haven't added the taxes on it, I haven't added the service charges or anything else. So my bill, depending upon the country, service provider, XYZ, numerous factors, government facilities, subsidies, by the end of the day, the bill actually what I'm going to get will be charged for all these factors. So I may get, let's say, a bill that is larger than, let's say, more than $200, but the electricity cost that I've used up would be 150 approximately. Do you understand this point? Any issues?
Yeah.